Good morning, good afternoon, wherever you may be in your day. As always, thank you for choosing to make chemistry part of that day, and it can only get better when you do that. All right, so, using molarity. Let's make a solution. And we're going to do two of these, one from a solid, one from a liquid. Let's start with the solids. Why? That's what we do more of. Okay. Before we make a solution, let's talk a little bit about what we need to do before we even step foot in a lab. And a lot of times these planning steps get lost. I teach capstone upper division labs, and you have we get thrown with some of these basic decision-making process of how much should I make, what size container do I need, and all these things that go into it. So before you even consider making a solution, there's really three things that you need to know. Two for making the solution, and one just as a general practice. One is, how much are you going to make? And I would say this, if you need 49.9 milliliters of a solution, don't make 50, make 100, in case you mess up the first time, in case you need an extra trial, those types of ideas. You know, maybe you want to make 150% of what you need. In case you lose a little in transferring, you need to rinse some, spill a little, those kind of ideas. So you don't want to get crazy and make 20 times what you need. But, you know, do think about that. How much do I need? That's typically a volume, milliliters, liters. What concentration do I need? If I'm trying to mimic my blood, I need a certain concentration of salt. Maybe I need 0.1 molar sodium chloride, 0.14, something like that. Maybe I want to mimic the ocean. Maybe I, just want to have 1 molar for standard units. So think about those things. What do I need? And then we should always consider safety considerations. And remember, things like don't work within 6 inches of an edge, and basic things like you should have gloves on anytime you touch a chemical, any unknowns, consider them toxic, etc., etc. But you should look up the safety considerations for any chemical that you use. All right, so let's just focus on the dark blue at the top, and then we'll get into the details. All right, so explain in detail how you would make a 100 milliliter solution of 0.1 molar sodium chloride. So, first thing we have to do is we got to be able to find sodium chloride to make sodium chloride. So you can see we have our two pieces. We have our how much do we need and how concentrated. And since this is a calculation, we don't have to really worry about safety considerations. But salt water is fine, so really nothing to worry about there. Okay, so we have to find sodium chloride. And if I were to look for this, I'm going to look for it on a shelf, in a bottle, in a spot either labeled with sodium ions or chloride ions or ionic compounds. How do I know? Well, that's an ionic compound. And how do I know ionic compounds are going to be in a jar and they're going to be solid? Well, because it's a really strong bond. We talked about that. Lots of ions piling up. It's an empirical formula. It's really 1 million sodiums stuck to 1 million chlorides, and they're all interlaid with each other and stuck together. So these are things that are going to be almost universally solids, and they're going to be powders, and a lot of times they're stable this way. So you go into the lab, you find the bottle that says sodium chloride, you pick it up. And of course, well, I don't know how much I need. That big M is blank per blank. It's moles over liter. So none of those are, I don't have a scale that does moles. I can't just pour salt crystals in and expect to get liters of that. That doesn't make any sense. So what I can do, and what we do is we weigh out things and we get a mass. So the real question is, how many grams of sodium chloride am I looking for? So this is going to be a calculation, right? For any of these things, you're going to have to weigh out any ionic compound. You're going to start with calculating the mass that you need, because that's something we can practically do in the lab. Get the mass of the salt and put it into a volumetric flask. And I'm filming these at home, and I don't have a volumetric flask with me. I apologize for this. But they kind of look like this. Ball on the end, glass tube, little stopper you can put on the top. That's probably about the right size for a 50 milliliter volumetric flask. They are designed to do one volume and one volume only. They will have a little mark somewhere, usually very light, etched into the neck. Sometimes it's higher and lower, even from the same company in the same box. They make sure that each volume is precise. And if you have your meniscus of your solution sitting right on that line, at the temperature noted in the small print on the flask itself, which is usually 25 degrees Celsius, you will see that that is exactly the volume listed. So we would grab what we call a 100 milliliter volumetric flask. It would be one of these that has a line on the neck, and it says in writing 100 milliliters on it. Can't miss it. it would have 100 milliliters written literally on the flask. Grab that, you'd be fine. Okay, so take your 100 milliliter volumetric flask, bring it over to the balance, put it next to the balance, maybe put a piece of weigh paper down, and we got to figure out how much we need to weigh. Okay, so let's take a look at what we have. We always start backwards. I want to know how many grams of sodium chloride do I need for this calculation. So we have a number of milliliters and molarity, but again, when you do calculations, I don't want you to think about this as molarity. I want you to think of it as moles over liters. So which of these numbers is most related to grams or mass of sodium chloride? Milliliters of solution, moles of sodium chloride, or liters of solution? If you said moles of sodium chloride, pat yourself on the back. That is our starting point. If grams is on top, we certainly want moles of sodium chloride on top here, and this is going to be liters of solution. Now, let's take care of the top. We want to go grams to moles. That's formula weight. Moles is on top. Cancel it out. We put moles here. And we now have grams per liter, which is pretty good. Liter is a unit of volume. Do we have a volume of solution we can use? Absolutely. But is it in the units we want? No, so we have to change those units. So that's milliliters, that's liters, so let's change that. 1 liter to milliliter we can do. And now we can just use our milliliters to cancel out. And we've done our calculation. Notice, I did all the units and I put no numbers in. This is really the thought process we should use, and then go through. Okay, so 1,000 milliliters is 1 liter. 1 mole is, what is that, 58.44 grams of sodium chloride per mole. Again, just the mass of 1 sodium plus the mass of 1 chloride. And then our mole per liter is 0.1, and that's always with when it's blank per blank, the number always goes with the first thing. So if it's moles per liter, the number goes with the moles. So that's 0.1 mole per 1 liter. At this point, we just calculate it through, and we get 0.5844. Actually, that's too many significant figures. 0.4 grams of sodium chloride. This is something we can certainly reasonably weigh in the lab. And we can either weigh it directly into the volumetric flask, or we can, what they say, quantitatively transfer, completely transfer to the flask. You may rinse it. There are different techniques for that. I'll leave that for lab. So, this is a typical calculation. Anytime you see moles of molarity, or milliliters and molarity together, typically with the English word of, first step in that problem is always going to be to get moles. So we get rid of the volume, get the moles, or in this case I did grams first, and then we'd have our mass. So, we'd weigh our mass of sodium chloride into our volumetric flask. Then we'd fill it up about 2/3 of the way, and we want to dissolve it all. Why do we not fill it all the way up? Well, there's a couple reasons for that. It could get hot. If it gets hot, it'll expand. If it cools, it'll contract. Those are volume differences we do not want in our final solution. The other thing is we need room to dissolve it. And sometimes when you mix the solid and the liquid together, they either pack more efficiently or less efficiently. So again, they can expand or contract. So all these things have to even out before we actually want to set the volume, which is always solution and not water. So we can't just add 100 milliliters of water. That doesn't work. So we're going to fill this up about 2/3 of the way, 3/4 of the way. It doesn't really matter. Fill it up enough, swirl it, dissolve it. Make sure it's at room temperature. Once it's all dissolved, it's clear, room temperature. Fill it the rest of the way up so that the meniscus sits right on that line. Cap it. Don't use your thumb. Going back to safety. Cap it. And then flip it 20 times. And it really actually takes 20 inversions, and then the bubble go up and the bubble go down, to really get a full mixing. And there you have it. You are now an expert in making solutions from salts. Thank you very much for your time, and I hope you found this informative.